Now to discuss the transport of molecules by diffusion. Let's consider what it would be useful to know when we are trying to solve diffusion problems. It would be useful to know the number of molecules and how fast they will turn up, i.e. over a unit of time and over what area. This is called the flux of the molecules. We'll define this more accurately in a moment, but the total flux, as a result of the random walk nature of the molecules, depends on a property called diffusivity, the concentration of the molecules, and is inversely proportional to the distance that the molecules have to travel. Let's spend a little time here understanding the transport properties of molecules, leading to an understanding of Fick's law of diffusion. To do this, let's consider a cylinder containing a non-uniform distribution of molecules. We can define two regions, region 1 and region 2, and we can also define two positions. Let's call this position at region 1 0, and this position at region 2 x equals delta x. Finally, we can define a concentration of molecules at region 1 as C1, and the concentration of molecules at region 2 C2. Concentration is the number of molecules per unit volume. It can be given as a straight number, or we can use the concept of moles again to reduce the size of the numbers that we have to deal with. Now we can define a diffusion velocity, which is denoted by this large Vd. This is using speed equals distance over time again, so we can say that the diffusion velocity equals delta x on t, where x we can replace from our previous video as delta x squared on lv. So therefore we can write that the diffusion velocity equals lv on delta x. Now to the flux. So the number of molecules arriving per unit time, per unit area, is called the flux, and we use this symbol J to denote flux. We can define a flux of particles arriving from region 1 to region 2 as J1, where J1 equals the diffusion velocity times the concentration in region 1 divided by 2. So this factor of 2 here is important. This takes into account that at any time 50% of the molecules will be moving away from region 2 at the same time that the other 50% of the particles are moving towards region 2. Remember, this whole process is predicated on the random thermal motion of the particles. Now we can also define a flux for the number of molecules arriving from region 2 to region 1, and we can call this J2. So similar to the previous page, J2 equals Vd C2 divided by 2. So putting this all together, we can calculate the total flux J. J equals J1 minus J2, which equals the diffusion velocity minus the change in concentrations divided by 2. So as Vd equals Lv over delta x, write out the equation now as J equals Lv times the change in concentration, C1 minus C2, over 2 delta x. Now we're going to define an additional term here as Lv on 2. So this is the mean free path times how fast the molecules are travelling divided by 2. This is called the diffusivity, d. So finally we get to Fick's law, where the total flux J equals the diffusivity divided by delta x, the distance, multiplied by the difference in the concentrations, C1 minus C2. And this is called Fick's law, which was of course developed by the German doctor and part-time physicist Adolf Fick in 1855. Let's talk a little bit more about the diffusion coefficient. The coefficient of diffusion, or diffusivity, is related to the molecular velocity v and the mean free path L, as we said before. So we wrote that d equals Lv on 2. What would be the units of this property? Well, we can work that out fairly easily by adding in the units of mean free path, which is meters, v, which is meters per second, and we end up with meters squared per second. Just to note that the factor of a half here, as we talked about before, is for systems that are only considering diffusion in a single direction. In 3 dimensions, i.e. across a membrane, we would have the diffusivity equals Lv on 6. Often when you're given the diffusivity in a problem, this has already been taken into account. This slide here shows a table of diffusivity constants. These are values of D in water at room temperature. Now let's consider diffusion through a membrane. Again, we'll draw a cylinder with 2 different concentrations of particles, and now we have a membrane going through the middle. Now the net or total flux, J, flowing through this membrane is given in terms of P, which is the permeability of the membrane. The permeability takes into account both the thickness of the membrane, delta x, and the diffusion constant D. So it's really the same as we saw previously in Fick's law, except now we've replaced d and delta x by the permeability of the membrane. So there's no new equations here, but it's still useful to think about the diffusion through a membrane in this way.